Welcome to Tinyhouse, Newline's first masterclass. In this masterclass, we'll build a production-ready application using React, GraphQL, TypeScript, Mongo, and Node. This masterclass is a project-based hands-on experience, and we're incredibly excited to have you with us. We're your instructors. I'm Hassan, a front-end engineer based in Toronto, and I've helped author Full Stack View and a series of other publications under the Full Stack and Newline umbrella. I've also been working with React, GraphQL, and TypeScript for a number of years now to build large-scale production applications.
Hi, I'm Jing, also a developer based in Toronto. I've been working with React, Node, and MongoDB for the past few years on building apps ranging from hobbies to startups. We've broken the course down into two parts. In part 1, we'll be introducing all of the core technologies you'll need to develop a full-stack web app. We'll learn about Node, TypeScript, GraphQL and Apollo, MongoDB, and React. We'll use these technologies to build a web app that presents listing data, which is kept in a Mongo database and is accessed through a GraphQL API. We will also introduce a UI framework to make our app more presentable.
In part 2, we'll be taking everything we've learned from part 1 to now focus on building an actual production-ready app. We'll maintain and use all the things we've learned in part 1, but now focus on building the Tinyhouse application. We'll discuss the relationships and flow within our app, as well as handle topics like Google OAuth for sign-in, use Google's Geocoding API to resolve location-based searches, Stripe for handling payments, image storage with Cloudinary, deployment, and a lot more.
We are excited to launch our course on the Newline platform. You'll have access to all source code, screencast videos, and manuscript. In order to reinforce learning material, the course also contains quizzes, project challenges, lecture slides, and a lot more.
We're incredibly excited to have you, and we'll see you in the course. We recognize everyone has their own setup when it comes to the development working environment. With that being said, in this lesson, we'll be discussing some of the tools and items we'll use in this course for you to either follow along with or find an appropriate replacement. In addition, we'll discuss some of the things you'll need to have to proceed through the course without any issues. The code editor we'll be using in this course is VS Code, otherwise known as Visual Studio Code. Though you're welcome to use any code editor of your choice, we encourage using VS Code for some of the advantages it provides with a minimal configuration setup. VS Code includes TypeScript language support out of the box to help display TypeScript compiler errors and warnings right in our editor, which is especially useful. In addition, as we proceed through the course, we'll periodically be installing extensions to plug additional and useful functionality in our editor workspace. We'll have 2 extensions installed from the get-go, with others we'll install at other points of the course. The more important one is we'll have the Prettier extension installed. Prettier is a code formatter that helps enforce a consistent style throughout our code. We encourage you to install Prettier as you are about to begin. As a side note, if you're interested in the editor scheme we're using, this comes from another extension we've installed from the beginning, called Monokai Pro. To install extensions in your editor, you just head to the Extensions tab in your VS Code editor and search for extensions in the marketplace. You can use any terminal you would like to navigate through project directories, run commands, etc., but we'll be using the iTerm2 terminal emulator available to us in Mac operating systems. Though we will mention this in one of our very first lessons, you will need to ensure you have Node downloaded in your working machine. We encourage you to download Node from the Node.js website and ensure you have NPM available as well. We'll be using Google Chrome as our browser of choice for the entire course when we build our client applications. You're welcome to use any browser you prefer and may be used to, but our preference would be either Chrome or Firefox for their great development tools. To proceed through the course, you will need a valid and working internet connection. Throughout the course, we'll be working with tools available externally, whether we're installing packages, interacting with our database on the cloud, or working with remote APIs. To avoid having any issues, do ensure that you work with a secure internet connection.
Hi there. In this module, we'll be creating a Node server from scratch. Then we'll use Express to bootstrap a simple web server. In the end, we'll introduce the benefits of TypeScript and integrate TypeScript into our Node server.
In fact, the details within this module will introduce Node and explain how Node is different to other web server technologies, run a simple JavaScript file with Node, create a server with the help of the popular Express package, use Nodemon as a development tool to help with automatic reloading of our code, introduce TypeScript and explain the benefits of using it, add TypeScript to our server project, and see how we're able to compile a TypeScript project to valid JavaScript, install and use ESLint as our development code linting tool, and finally use mock data to create a get and post route within our server to mimic how RESTful APIs are to usually behave. Node is a JavaScript runtime environment that can run on different platforms: Mac, Windows, Linux. What this means is JavaScript, which is originally created to run inside a web browser, can now be run on any computer as a web server. Node was originally released in 2009 by Ryan Dahl as a response to how slow web servers were at the time. This is because most web servers would block the input-output task, which would lower throughput. Node changed this model by making all input-output tasks non-blocking and asynchronous. Non-blocking just means that a request from a certain interaction can be processed without waiting for the prior interaction request to finish. This allowed web servers to serve countless requests concurrently. Here's an example taken from the main Node website in comparing code between the synchronous blocking state and the asynchronous non-blocking state. This example covers the use of the Node file system, which allows us to work with the file system in our computer. The file system module is included by stating require fs, which is short for file system. The read file sync method is used to read files in the computer, with which here we're stating that we want to read a file named file.md. The read file sync method is synchronous. So here, the more work function would only run after the entire file is read in the process above. This is an example of synchronous blocking code. The second line here, read file sync, blocks the code from continuing until its process is complete. As we've mentioned, Node allows input-output tasks to be non-blocking and asynchronous. So in this example, we're doing the exact same thing, that is to say reading a file named file.md and running the more work function, but we're doing so in a non-blocking setting. This is because we're now using a read file method, which is asynchronous and allows the use of a callback function. This callback function won't run until the former function read file is complete. In this case, read file doesn't block code since the more work function will be run while the file is being read. Whenever the reading of the file is complete, the callback function will then run. The ability to have the more work function be run alongside the reading of a file was a primary design choice in Node to allow for higher throughputs. Callback functions, promises, and the capability to use async await are all the tools that Node gives us to have input-output tasks be asynchronous and non-blocking. If you've built any web application within a Node environment, you've already come across something known as NPM. NPM, short for Node Package Manager, is two things. It's an online repository for the publishing of open source Node projects, and it's a command line utility for interacting with the NPM repository. Now, the ecosystem of third-party tools that can be easily installed in a Node application makes Node a very rich ecosystem. This also ties in with how we build applications in Node, by introducing just the tools and libraries we need in an app. One awesome benefit of using Node is that Node makes capable the building of universal JavaScript applications, often also known as isomorphic JavaScript. These are applications that have JavaScript both on the client and the server. And this is exactly what we'll be doing in this course. Node is built against modern versions of V8, Google's JavaScript and WebAssembly engine, which helps ensure Node stays up to date with the latest ECMA JavaScript syntax. To install Node, all we have to do is go to nodejs.org and download the latest LTS version of Node, which is recommended for most users. Once downloaded, we just follow the on-screen instructions to complete the installation. An easy way to verify if Node is installed in your computer is to run the following command in the terminal, node-v, which will tell you the version of Node installed. NPM is installed as part of Node, but to also verify its availability, we can check for its version number with npm-v. On the left-hand side, we have our Visual Studio Code Editor, and on the right-hand side, we have our terminal. In our VS Code Editor, we've already added in an empty folder called Tinyhouse_v1. And in our terminal, we've navigated down to that very same folder. Tinyhouse v1 would essentially be the directory where we build the app for the first part of our course. To get things started, we're going to create a subfolder called Server. This Server subfolder would essentially host the server portion of our app. We'll go ahead and have an index.js file be created within this Server subfolder. Now, for our very first attempt, we're going to see how we could use Node to run some JavaScript code. And the first code we're going to write is a simple console log message. We're going to attempt to log something into our terminal console. And the first thing we're going to look to log is a simple string that says hello world. Next, we're going to create two variables. We're going to create a variable called 1, and we're going to create a variable called 2. Notice that we've given numerical values to these variables according to their name. So 1 is given a numerical value of 1, and 2 is given a numerical value of 2. We're using the const keyword here. Const is one of the ES6 preferred ways of defining a variable. It essentially allows us to specify variables and give them values in which they can't be changed through reassignment. Finally, we're going to fire off another console log message, and in this case, we're going to fire off an interpolated string. We're going to state that we want to see 1 plus 2 is equal to the sum of the values of the variables we've defined above. Notice that we're using backticks here, or ES6 template literals. This allows us to essentially embed expressions within our string. So what we attempt to see here is a message that says 1 plus 2 is equal to 3. Now in our terminal, let's run this JavaScript code. And to do so, we're going to use the node command. The node command can take an argument for essentially the location of the file in which you want to run the code. Since we're already within the tinyhouse_v1 directory, we want to run the index.js file. So we'll say node server/index.js. And when we press enter here, we can see the two console log messages that we fired up. Hello world, and 1 plus 2 equals 3. What we've done so far is use Node to simply run a JavaScript file. Now we're going to look to create a Node server. A server is software or even hardware that aims to provide functionality for client requests. Large-scale applications we use day to day, such as Airbnb, Uber, Instagram, YouTube, all have servers that serve data to their respective client apps. These could be running on their phones and even computers to display the data to users. This is a very simple explanation of what a server is. Node comes with an HTTP module that provides the capability to create a server. We're going to create a very simple Node server, and if you haven't done so before, you'll notice how surprisingly little code is needed to make this happen. The first thing we're going to do is create a package.json file. The package.json file is an important element of the Node ecosystem and is where one can provide metadata about an app, list the packages an app depends on, and create scripts to run, build, or test the app. We'll create this package.json file at the root of our server project directory. A package.json file must contain a name field and a version field. Name and version are pretty self-explanatory, and they dictate the name of the application package being built and the version of that particular package. We'll name our application package Tinyhouse v1 server, and we'll give it a version number of 0.1.0. Next, to help us prepare a Node server, we'll install a third-party library known as Express. Express is an incredibly popular framework for Node designed for building servers and APIs. To install Express, in our terminal, we'll navigate into the server folder and then run the npm install command followed by the name of the package we intend to install, which in this case is Express. When complete, npm will fetch Express from its repository and place the Express module in a folder called Node Modules. When we now run our Node application, Node will look for the modules that are required in the Node Modules folder before looking into the parent directories and global installs in which packages may also be available. We can also notice that the package.json file has been updated to include Express as a dependency. For anyone else downloading our directory, all they need to do is run npm install to install all the modules listed in the package.json file. You may also notice a package lock.json file be automatically generated. The package lock.json file stores the exact dependency tree that highlights the dependencies installed from the package.json file at a certain moment in time. This file was first introduced in npm version 5, and it serves to ensure teammates and deployment processes are all guaranteed to always install the same dependencies, as well as aim to convey greater visibility in changes that are being made to the app's dependencies. The package lock.json file should always be committed alongside all the other files to source code, but will never actually directly touch this file. It is automatically generated. Cool. We'll now look to use Express to instantiate a Node server. We'll first move our index.js file to a source folder that's going to be located within our server application. We'll denote this source folder as src. Next, we're going to remove everything we've written before to have a blank slate for where we're going to create our Node Express server. The first thing we're going to do is we're going to require the Express module. And we're going to basically require that module and assign it to a variable labeled Express. Next, we're going to create an Express server instance by running the Express function and assigning that instance to a constant variable labeled app. We're then going to create a port constant variable with which we're going to specify the intended port number we'd want the server to run. We'll state this port number to be 9000. Now with app being the server instance, we can take advantage of Express routing and use the app.get function to associate a path with an endpoint function. So here we can essentially say that when we receive an HTTP GET request to the index routes denoted by just slash, we can attempt to respond by simply sending a hello world string. The endpoint function provides a request and response object as parameters. Request is an object containing information about the HTTP request, while response is how we send back the desired response. Here we'll keep it simple by saying response.send, a simple string that says hello world. We'll finally state app.listen, which is a function that Express provides to allow us to create the node server at a specified port. Here we can just simply pass in the port constant variable we've defined above, which will say that our actual server is going to run on port 9000. And then for convenience, we'll use a simple console log message to basically tell us that our app is actually going to be successfully run in the appropriate port. Like in the previous module, we can run this JavaScript code we've written by using the node command. So in our terminal, we're already located within the server folder. So we can now simply reference the source index.js file directly. So first, we'll use the terminal clear command to clear the logs in our terminal. And now we can use the node command to run our index file. Though we can say source/index.js to be explicit, we're also able to simply do node source, with which it's able to recognize that we want to run the index file within the source folder. Now that we can actually see when successfully run the console message that we've generated. This is helpful in telling us that, hey, this server is now successfully running and you can find this server in this particular path, localhost 9000. When we head to our browser, when we actually navigate to localhost 9000, in this particular case, I have it open, so I'm simply going to refresh it. We can see the hello world message that's going to be sent back to us. This is because we're in the index route, localhost 9000/, and we specified in our express routing that in the index route, that is to say, when we attempt to get information from this route, we want the response to simply return the string of hello world. And we can see that this successfully works. When developing our server application, there are going to be a lot of changes we're going to make to our code. We probably don't want to stop our running server and restart it every single time we make an update. Wouldn't it be nice if there was actually a third-party tool that sort of just did an update for us or reran the server whenever we made a code change? Well, there is, and it's called Nodemon. Nodemon is a tool that would monitor changes in our source code and automatically restart our server whenever a change is made. So to install Nodemon, we'll first exit the server we have running and then run the npm install command. In this case, however, we're going to add in another argument that is known as the -d flag. -d is a shorthand version of --save dev. And essentially, what it basically states is that we want to install this particular package as a development dependency. After Nodemon is installed, in our package.json file, we will actually see that Nodemon is listed as a dev dependency. Now we'll look to create a script in our application that can run the server with the Nodemon command. In Node applications, we're able to define Node script commands that are expected to be run in an app within a script section of the package.json file. Having scripts in our package.json file helps us avoid typing long commands manually on the terminal. What we'll do here is create a new script called start. This start script will be responsible in running our node server. But in this case, we're going to use the Nodemon command to do so, since Nodemon is now available as a dev dependency within our application. Just like the node command, we can just simply reference the location in which we want the node server to actually run. In this particular case, we'll reference the source folder, which will contain the index.js file, which has the JavaScript code that is to be run. We'll save the package.json file, and now in our terminal, to simply run our server, all we have to do is run the npm run start command. By doing so, we can see that Nodemon actually outputs some messages to the console. It tells us the version of Nodemon being used, and some other messages such as the ability to restart at any time, and the location in where it's watching. At the very bottom, we can see that the console log message we've specified in our index file is also being outputted. That tells us that our server is now actually being run at localhost 9000. Now, if we head back to the index.js file and attempt to change anything in this file, such as let's assume I want to change this hello world message to another string like hello again. By just saving this file, we can see that Nodemon detects this change and actually tells us that it's restarting due to changes and starting the same folder we specified before, the source folder. And then we can see the console log message be specified once again. This is really good because now we don't have to actually manually exit and restart the server. Nodemon is a fantastic development dependency since it watches for changes and simply restarts the server whenever there's changes being made. For now, we'll just simply reset this message back to hello world. JavaScript is considered a weakly typed language. And what this means is that JavaScript gives us the ability to assign one data type to a variable and later on assign another data type to that same variable. Let's sort of see an example of this. In our index.js file, we're going to sort of replicate what we've done before by creating two variables and sort of trying to show the summation of those two variables. So in this case, we'll create a constant variable called 1, give it a numerical value of 1, a constant variable called 2, give it a numerical value of 2. And now in our index route, instead of sending a hello world message, what we'll try to send is an interpolated string that says 1 plus 2 is essentially equal to the sum of the variables we've defined above, 1 and 2. Nodemon will restart our server, and when we head to the browser, refresh what we've done, we'll see the message that we expect to see. 1 plus 2 equals to 3. However, now let's go back and attempt to reassign the value of one of these variables. We'll pick the variable called 2. Since we're reassigning the value, we have to use the let keyword here. And in this case, we can say 2 is going to now equal to a string, another data type, and we're going to give this particular string value called 2 as well. When we now save our application, Nodemon runs again, everything looks good, but when we head to the browser, refresh what we've done, we can see something else happens. In this particular case, we don't get the summation of two values. Instead, we get the number 1 sort of assigned and placed right beside the text of 2. Now, why is this happening? This makes sense. JavaScript is unable to sum two different data types. So in this case, it simply goes through the easy way and says, okay, if you want me to add these two values, I'm going to simply place them side by side. So we've defined the variable 1 to be the number 1, and initially we defined the variable 2 to be the number 2. Only after did we reassign the variable 2 to be a string value called 2. Though we did this on purpose, we can also assume that this could also happen sort of accidentally, since we don't actually guard for the fact that the variables 1 and 2 have to be number values. In this case, JavaScript executed without any errors or warnings. In other cases, our code would most likely actually error if we attempted to manipulate and use a variable without recognizing that it had an incorrect type. Imagine we deployed code like that to a production app. This could obviously lead to production issues. This is why TypeScript was created. TypeScript is a strongly typed superset of JavaScript that was introduced in 2012 by Microsoft. It was designed to make code easier to read and understand. It was designed to help avoid painful bugs that developers commonly run into when writing JavaScript, and it was designed to ultimately save developers time and effort. It's very important to note that TypeScript is not a completely different language. It's just a typed superset of JavaScript that actually gets compiled down to plain JavaScript. It works on any browser, any host, any OS, and is completely open source. The key difference between static and dynamic typing, that is to say JavaScript and TypeScript, has to sort of do when the types of the written program are being checked. In statically typed languages like TypeScript, types are checked at compile time, which essentially means when the code is actually being compiled. In dynamically typed languages like JavaScript, types are checked at runtime, which means when the code is actually being run, which is why in the example we've had before, we weren't able to verify what would happen only until we actually ran the application. TypeScript is a development tool. Clients and servers don't recognize TypeScript code when run. This is because the static types that we can define in TypeScript actually get stripped during a compilation process that transforms the TypeScript code into valid JavaScript. Adding types is like sort of keeping units consistent when performing a math equation. Without TypeScript, you have to mentally keep track of units. For example, in the example we've done before, we sort of had to mentally track that if we wanted to sum these values, the constant variables 1 and 2 should be numbers. Oftentimes, assigning values to the wrong units could actually have pretty big consequences. In fact, there's a CNN article in 1999 that actually states that NASA crashed a $125 million probe because of incorrect unit conversions between the English unit measurement and the metric system. Now, this is obviously not a perfect analogy, but it does go to show that consistency is incredibly important. And this is what TypeScript aims to do for JavaScript. It aims to keep your code consistent by statically determining the types of everything we define and create. To configure our Node server into a TypeScript project, we'll need to install certain TypeScript development dependencies. Though there's a few tools that exist, we'll install the latest versions of the TypeScript and TS Node libraries. In our terminal, we'll exit the server for now, clear the terminal console logs, and now simply npm install the TypeScript and TS Node packages as development dependencies. TypeScript is a core TypeScript library that will help us compile our TypeScript code to valid JavaScript. TS Node is a utility library that can help us run TypeScript programs directly from the terminal. Next, we must create a tsconfig.json file. The tsconfig.json file is a basic JSON file that should be created at the root of a TypeScript project. This file is where we can customize our TypeScript configuration and guide our TypeScript compiler with options required to compile the project. To customize and edit our compiler options, the tsconfig file expects us to specify and declare a compiler options field. There are a large number of options we can dictate and control in our compiler, all of which can often be seen in the TypeScript handbook in their main website. We're not going to go through every different option and the reason behind them, but instead we're going to dictate the ones we need for an app and simply introduce them as we explain it. The first option we'll declare is the target option. Target allows us to specify the target JavaScript version the compiler will output. Here we'll declare a target output of ES6 since Node supports a vast majority of ES6 features. Next, we'll declare a module option. Module allows us to refer to the module manager to be used in the compiled JavaScript output. Since CommonJS is the standard in Node, we'll state CommonJS as the module option. Next, to specify the location of files of where we want to actually declare TypeScript code, we'll use the root directory option. We'll give a value of ./source, which would essentially tell our compiler that we intend to have all our TypeScript files within the source folder and with which we want the compiler to actually compile. Next, we'll use the output directory option. Output directory allows us to specify where we'd want the output of compiled code when we decide to compile our entire TypeScript project into JavaScript. Here we'll specify a new folder that we'll create when this happens called build that will be kept at the root of the project directory. To help compile our CommonJS modules in compliance with ES6 modules, we'll need to introduce the ES module interrupt option. And give it a value of true. Finally, we'll be able to apply the strict option. Also provide a value of true. Strict allows us to further enable a series of strict type checking options, such as no implicit any, no implicit this, strict null checks, and so on. There's a lot more options and configurations we can make, but this is all we'll need for now. Now, if you don't fully understand what's actually happening here step by step, there's no need to worry. You're more than welcome to check the TypeScript handbook to get a better understanding of what each of these fields do. But the key takeaway here is the tsconfig.json file allows us to control the options and configuration of our TypeScript compiler. And most importantly, we're specifying that the root directory of where our files are going to have our TypeScript code is going to live within the source folder. And then we're applying the strict option, which allows us to apply a series of strict type checking options dynamically by just specifying this particular field. In our tsconfig file, VS Code is sort of showing a particular error that might be showing up. Now, this error is most likely attributed to the fact that we don't actually have any TypeScript files within the root directory we've specified our compiler options to actually take into account. Most likely, once we start to introduce our TypeScript files, this error should most likely go away. So we won't pay any attention to it right now. So now we're going to look to install the type declaration files for certain dependencies that exist in our app right now. Let's explain this a little more. For us to use third-party libraries, such as Node, Express, etc., and have the full power of TypeScript, those libraries should also have dynamic types. Unfortunately, some of these libraries are only written in native JavaScript, like Express and Node, or they could also be written in other JavaScript extensions, like CoffeeScript. This is where TypeScript actually allows us for the creation and use of something known as declaration files, which are simply files that allow us to describe the shape of existing JavaScript code. We could go ahead and create declaration files on our own for Express and Node and any other library you want to use, but that can be pretty tedious and take quite a bit of time. This is why in the TypeScript community exists a repository known as definitely typed. The definitely typed repository holds TypeScript declaration files for a large number of packages we tend to use and is entirely community driven. So if you ever find yourself using a package that doesn't have a declaration file publicly available, you're more than welcome to contribute it into this repository. In our application, we're currently using the Express and Node libraries. These libraries aren't TypeScript libraries, so we'll need to install the TypeScript declaration files for these two libraries. We'll install them as development dependencies. Now, to install the declaration files from the definitely typed GitHub repository, we can install them under the @types namespace, which refers to the libraries kept within that particular repository. The very first one we'll install is the node declaration file. And the second one we'll install is the express declaration file. With these packages installed, we can now start to modify our code. The first thing we're going to do is we're going to rename the index.js file to be a file denoted by index.ts. Index.ts, or just TS files in general, is the file extension used to denote TypeScript files that will eventually be compiled to JavaScript. Just from that alone, we can see that VS Code actually shows us some warnings. We'll get to those in a second. The first thing we're going to do is, instead of using the traditional require syntax, we can now utilize the import feature that ES6 provides to import the express module. Though Node supports a vast majority of ES6 features, the one thing it doesn't currently natively support is the import syntax. And this is one advantage of using TypeScript. TypeScript will compile our code to valid ES6 code that Node recognizes. So when we actually develop our code with TypeScript, we can take advantage of some pretty new features from JavaScript. Cool. So now, when we actually hover over this particular warning, we can see that our VS Code IntelliSense warns us that the TypeScript compiler would most recognize an error here. It tells us that the type 2 is not assignable to type number. This is because it recognizes that when we instantiated the variable 2, it was of the number type. As a result, we shouldn't be allowed to reassign the value of the variable to a different type. Just from the simple changes we made alone, we can already take advantage of TypeScript right here already. So with that said, let's actually remove what we've done here. And let's just keep our variables as numbers for now. The headline feature of TypeScript is static typing. Instead of having our variables 1 and 2 be inferred as numbers, we can explicitly define the type as number. To do so, we'll place a colon right after where we actually declare the name of the variable. And here's where we can specify the type of what we expect these variables to be. In either case, we'll say they should be of type number. TypeScript also allows us to apply a number of different primitive types. Assume we had another variable called 3, with which we can specify something like the Boolean type and provide a Boolean value. We could apply the string type and provide a string value. We could apply the null type and provide a null value. We could apply the undefined type and pass in an undefined value. And we can even apply the any type and specify any value. There are other basic types as well, such as the array type, the enum type, the void type, etc. We'll investigate a lot of these other different types as we progress through the course. In any case, when we explicitly define the type of a variable, we have to provide the value that matches that type. This is through initialization or even through reassignment. For example, for our 1 and 2 variables, assume for our very first variable we wanted to give it a string value. TypeScript compiler will complain, and the VS Code IntelliSense is smart enough to actually warn us right in our editor. It basically tells us that the value you're trying to provide doesn't match the type that you specified this variable should be. The only unique type in TypeScript is the any type. Any allows us to explicitly define a variable with any type, hence the name. Now, these variables don't give us the capability TypeScript provides because we can reassign this particular value to anything that we want. So though it could be used when needed, it should be used sparingly because we don't actually get the power of TypeScript when we use the any keyword. Let's remove this 3 variable for now. If we take a look at the tsconfig file in our project, we can see that warning we saw in our editor doesn't appear any longer. This satisfies the assumption we made that that warning probably arose due to the fact that we didn't have any TypeScript files in our project. Cool. With that said, now let's look to see if we can actually run our application even though we've added TypeScript into our app. Let's take a brief look into the package.json file. Technically, this start command should work as intended because we intend to run the TypeScript code, i.e. the Node TypeScript code within the source folder. However, if we actually run this command currently, it's going to assume to look for a JavaScript file in our source folder. As a result, we'll look to be a little explicit here and state that we want to run the code in our source.index.ts file. With that said, let's head over to the terminal and now run npm run start. And there we have it. Our project now runs despite us doing very minimal changes to actually invoke how we want to run TypeScript code. In our logs, however, over here, we can see the message tsnode source/index.ts. This tells us the tsnode package in our application is now being used to run the TypeScript app directly from our terminal. This is in thanks to Nodemon. Nodemon invokes tsnode whenever a TypeScript file has been changed. tsnode under the hood does a bunch of checks to verify that all our TypeScript code is good and then compiles our TypeScript code to JavaScript. If there's ever a TypeScript error, Nodemon will actually crash. Let's actually see this. If we intend to make our one number variable a string even though we explicitly define it to be a number type, if we save our file right now, Nodemon will attempt to actually start our server, but it would crash and we would actually see a TypeScript error stating that it's unable to compile TypeScript, and it actually gives us the error where the issue arises. Cool. So let's bring this back to being a number, and let's save it one more time. Nodemon will restart our server. We can see that our app runs at localhost 9000, and now by heading to localhost 9000, refreshing what we have, everything should work as intended. This is a great example of how TypeScript helps to check any errors or issues in our code during compile time, not during runtime. And this was best seen because the moment we specified a string value to a number type, the compiler errored even before we attempted to run our application. Now, though this is a very simple example, and you can probably get away without using TypeScript, the importance of TypeScript really comes in for very large-scale applications that have multiple developers working together. At any moment in time, if the TypeScript compiler thinks you're doing something wrong, it would warn you most likely in your editor, and then even though it would actually error during compile time, which gives you that very quick feedback that's incredibly helpful for developers to move quickly and ensure they're not introducing bugs as they start building more and more features in an application. Though our application is now suited for TypeScript development, to have our code be ready for production, it first must be built as a JavaScript project. This is perfectly okay because TypeScript was only created to help developers during the development phase. Once the app is in production, known bugs should have all been fixed. To achieve this, we're going to create a new script in our package.json file. And this script is going to be the build script. Build is going to be responsible in building, or in other words, compiling the TypeScript code in our project to valid JavaScript. And we can do so by using the tsc command that TypeScript provides. tsc takes an option known as -p, which is shorthand for --project. This -p option essentially allows us to compile the TypeScript code in a project that contains a tsconfig JSON file. The project option requires an argument of the project directory with which we can simply specify, in our case, /. This is essentially stating that the build command should help compile all the TypeScript code in the TypeScript project in which this package.json file currently lives in. We'll save the file, and now we can actually head to the terminal, exit the server, and attempt to build our actual TypeScript project by running the newly created build script, npm run build. When complete, we can now see a build folder has been introduced in the root of the server project. This build folder contains the JavaScript code for our index.js file that has essentially been compiled from the TypeScript index.ts file. If we really wanted to, we can actually run the JavaScript from this file directly within the build folder, node build index.js. And as you can see, we can see the console log message that's been generated from our code. So now this is essentially the bundle or the build that we'll use during deployment. Because once again, TypeScript is a development dependency. The moment we're ready to actually complete our app and have our app be deployed, we'll need to build our application, retrieve the compiled JavaScript code, and then finally place that bundle into any deployment process that we want. Other than that, we'll very hardly ever find the need to ever dive into the build code to see the generated compiled JavaScript code. Though VS Code includes TypeScript language support, which helps us pick up simple errors in our TypeScript code, we'll probably want to introduce more robust code checking. For example, assume we wanted a variable to never have the anytype. Now, TypeScript won't stop us here since any is a valid TypeScript type. But as a preference, we probably don't want to have code built in our app that has this particular type since it removes the benefits of TypeScript. This is where linting comes in, or more particularly in our case, ESLint. For those who don't know what linting is, linting, or sometimes recognized as code checking, is a process of running a program that will analyze code for potential errors. And when it comes to linting JavaScript and TypeScript code, ESLint is the most popular library to do so. It's configurable, easy to introduce, and comes with a set of default rules. To introduce linting into our app and take advantage of our code editor, we'll first install the ESLint VS Code extension. Once installed, we'll now go ahead and install a few other development dependencies we'll need to enable ESLint configuration into our app. We'll install the ESLint package. We'll install the @TypeScript ESLint parser package, and we'll also install the @TypeScript ESLint plugin package. ESLint package is the core ESLint library we'll use. The @TypeScript ESLint parser package is a parser that will allow ESLint to lint TypeScript code. And the @TypeScript ESLint plugin package is a plugin that, when used in conjunction with the TypeScript ESLint parser package, contains a bunch of TypeScript-specific ESLint rules we'll use in our app. Next, we'll introduce a .ESLint RC JSON file in the root server project directory. Similar to how the tsconfig file was responsible in configuring our TypeScript compiler, the ESLint RC JSON file will be responsible in configuring the ESLint setup of our application. Now, ESLint actually accepts different file formats for this file. We could use a .js format, a .yaml format, but we'll stick with a .json format. Next, we'll look to introduce a couple of options to our ESLint configuration. We'll first introduce a parser option. Parser would be to specify how we want to read and translate JavaScript code for it to understand. The default ESLint parser, ESPre, doesn't recognize TypeScript code. So we'll use the @TypeScript ESLint parser. @TypeScript ESLint parser is probably the most widely used and supported parser for TypeScript code and is the one we've just installed. Next, we'll define a parser options field. The parser options configuration allows us to specify the language options we want ESLint to support. By default, ESLint supports ES5. So here we'll define a ECMA version field, which allows us to state the version of ECMA script syntax we'll use in our app. We'll go ahead and say 2018 to allow for the parsing of modern ECMA script features. Here we'll also define a source type field. And we'll pass in a value of module. This allows us to say that we're using ES6 modules in our app. We'll then define the root level an extends field. Extends allows us to extend the rules from a certain package. In this particular case, we'll specify the TypeScript ESLint recommended package to extend. So we'll say plugin @TypeScript ESLint recommended. Next, we'll define an environment field. The environment field dictates which environment our ESLint script is expected to run. Every environment has its own set of particular global variables. So we'll go ahead and state that we're in the node environment. This will help us recognize, or help the environment recognize, unique node definitions. And then finally, we're going to define a rules field. Rules is where we can declare individual ESLint rules we want in our app. Here's where we can override the rules from the TypeScript ESLint recommended package we're extending, or where we can even introduce new rules. The TypeScript ESLint recommended package comes with a rule for indenting. Now, Prettier handles all the indenting formatting for us. So as a result, and for preference, we'll turn off any indent formatting rules. We'll explicitly turn off the indent rule by specifying indent off. And we'll also explicitly turn off the @TypeScript ESLint indent rule by turning that off as well. We'll now save our changes and we'll stop here for now. Similar to how you may not really understand what's happening in the tsconfig file, if you don't really understand every option here, that isn't really a problem. The main takeaway from this is that the ESLint RC.json file is sort of the configuration file for how we want to configure ESLint in our development environment. We specify a parser to basically tell ESLint to be able to parse TypeScript code. We state that we are basically looking to create pretty new JavaScript code, ECMA version 2018, and in terms of a large number of ESLint rules, we're going to extend an existing package or plugin known as TypeScript ESLint recommended. And then finally, we can customize the rules the way we see fit in our rules option right here. For now, we're simply turning off any indenting rules because Prettier is going to take care of formatting for us. If we head to the code in our index.ts file, we can't be sure if our editor is actually picking up and showing any ESLint errors. Well, currently at the moment of this screencast, the ESLint VS Code extension doesn't have TypeScript support enabled by default, and editor warnings are only being shown for JS files. To make this work, we'll need to add some form of information to our settings of our VS Code editor. I'm going to be opening the settings JSON file in my editor, and I've already added in a block of code that we're going to need to add. Essentially, we need to specify that we want ESLint to validate JavaScript code, JavaScript React code, TypeScript code, and TypeScript React code. We're adding in TypeScript React because we're going to be working with a TypeScript React project very soon. We've set autofix to be true here since this will allow for some auto-fix suggestions to be provided by the editor. Everything below is some of my personal configuration, but everything above here from ESLint validate is the actual field we'll need to be adding. In our instance, we still can't see any warnings or information from our editor. And we've realized this is because we've actually introduced a mono repo here called Tinyhouse_v1 that contains another folder in which we want its ESLint configuration to show up. We've noticed that the ESLint extension in VS Code doesn't behave very well in this scenario. So what we're going to do here is we're going to remove the import of the entire repository, Tinyhouse v1, and we're simply going to introduce the server folder from Tinyhouse. And by doing so, we finally see some editor warnings thanks to our ESLint extension. When we hover over one of the first two rules, we can see that this ESLint warning tells us that type number is trivially inferred from a number literal. Remove the type annotation. This rule is one of the ESLint rules dictated from the recommended TypeScript package we're extending, and it basically states that simple types such as number, string, boolean, etc. can be easily inferred, so it doesn't have to be explicitly defined. We like this rule as a preference, so we'll comply and we'll remove the explicit definition that these variables are of the number type. Next, when we hover over the function that returns the value for our GET request, we can see that there's an ESLint warning that tells us that this particular function misses a return type on the function. Just like how variables can be explicitly defined to have a type, functions in TypeScript can also be explicitly defined to have a type. Now, as a preference, we prefer to follow the same format and say if variables can oftentimes be inferred from its type, we'll prefer if functions can just simply infer the type and only be explicitly defined if needed. So this is where we'll actually configure a rule in our ESLint RC.json file. We're going to turn off one of the TypeScript ESLint recommended rules from the package that we're actually extending. We're going to turn off the explicit function return type rule. When we head back to see the function, we can see that ESLint doesn't actually give us a warning any longer since we've actually disabled that rule. And we're okay with doing so since that function type is being inferred. There's one more thing we're going to look at. When we actually hover over this request parameter in our callback function, we can see that VS Code is actually giving us a warning. This isn't an ESLint rule. This is a VS Code TypeScript warning that we've actually ignored. And it's basically telling us that this request parameter is being declared, but its value is never being read. This is a useful warning, but in our particular case, we have to do this. This is because we have to access the second parameter, the response parameter. So even though we're not using the request parameter, we have to define it first. To notify TypeScript that we're aware of this, but we're okay with ignoring it, we can actually prefix this argument here with an underscore. This brings us to the end of this lesson, and we won't actually be making any more changes to our linting rules in our server. There's one more important thing we should discuss before we close this lesson. When we hover over variables, parameters, functions, and when we actually see information that our editor tells us, this falls under a general bucket term that VS Code calls called IntelliSense, and we've mentioned this before. This feature that VS Code offers is a very powerful feature, especially powerful when working with a good ESLint setting and when working within a TypeScript development environment. Because not only are we able to hover and recognize issues and warnings, we're able to hover and also recognize the types that are being inferred for all the different variables, parameters, functions that can be used within an application. This development environment is especially powerful and especially cool, in particular when you start to introduce more and more features into an app. If you've never had the chance to work within a development environment like this, I highly encourage you to come in with an open mind because you may realize how much you actually enjoy building an application as things get more and more complicated thanks to the power VS Code gives us. Let's add a little functionality to our current minimal server. To get us started, we're going to introduce a mock array of data that we'll use and manipulate before we start to talk and address more appropriate data persistence. We'll introduce this mock array in a listings.ts file within our source folder. The mock data we hope to introduce is a collection of rental listings where each listing will have a listing title, image, address, price, etc. We're going to provide this mock data array as part of the lesson documentation, so we're simply going to paste it in here for now. This mock array contains 3 distinct listing objects. Each listing object has a unique identifier, a title, an image, an address, price, number of guests allowed, the number of beds and number of baths this listing accommodates, as well as a rating out of 5. This is purely fake data with fake addresses and copyright free-to-use images. When we hover over the listings variable, we can see that TypeScript expects to infer the type of our array, and this is because we've initialized this array with some data. It expects it to be an array, denoted by the square brackets at the very end, of objects that contain these properties. ID, title, image, address are all expected to be strings, price, and everything to the bottom till rating are expected to be numbers. What if we now actually change the value of one particular field, let's say title for the very first one, and change it to be a different data type, like a number? If we now hover over the listings array, we see something else happening. What we see is 2 objects being specified as types and a unique pipe symbol between these 2 objects, and then the array syntax at the very end. This pipe symbol denotes creating a union type in TypeScript and essentially states that for this particular array, each object could either be of the first type, this particular object that has title as a number, or could be this object in which title is a string. And this makes sense. We're not restricting this array to be anything. So TypeScript is basically inferring what this array could be. Could we ensure that the objects we declare in this array all conform to a single shape? For example, can we specify and ensure that the title field is going to be a string, and if we were to pass in a number, for example, TypeScript should warn us and the compiler should eventually fail? We could do this. We could do this by creating an explicit type that describes the shape of our entire listings array. But first, we're going to look into describing the shape of a single object. In TypeScript, there's 2 ways or 2 common ways we can achieve this. We could use a type alias declaration, or we could use an interface. Both can be used with minor differences between them, syntax-wise, as well as other more finite differences. We'll be discussing these differences at a later point in time, but for now, we'll resort to using an interface since the TypeScript team has historically used interfaces to describe the shape of objects. We'll expect each listing object to have a certain number of fields: ID, title, image, address, price, num of guests, num of baths, or beds first, num of baths, and rating. Just like how we've basically specified types for variables before, we can explicitly define the types of each field within the listing interface. So, for example, we want to say ID is going to be of the string type, and so would title, image, and address. Price would be of the number type, and so would be everything below: number of guests, number of beds, number of baths, and finally, rating. With our listing interface defined, we can now assign this type interface to variables and objects we can create in our app. For example, we could have very well created an object and said that this object should be of type listing. By doing so, we now actually have to initialize this object with the properties that this interface expects, an ID, a title, an image, and so on. We're not creating an object here though, we're creating an array called listings, and we want to sort of type define this listings array. To do so, we'll simply say that this is listing, and then we'll use the square brackets here to denote that this is an array type. This square bracket is sort of the more common way in TypeScript of defining array types. And the information we have just before the square brackets sort of denotes the items within the array. So in this case, we're saying that this is an array in which each item in the array should conform to the listing interface type. We very well could have said this is an array of strings, an array of numbers, and so on. But in this case, we're saying that this is an array of listings. The other approach of defining an array type in TypeScript is using the array generic and passing in the type of each item as a type variable. The TypeScript documentation actually shows both approaches, but our recommended ESLint package that we're using actually prefers the prior approach. We also do, so we'll actually go back to specifying that this is simply a listing and then using the square brackets to denote that it's an array type. We're also going to spend a decent amount of time discussing what generics are, so what's actually happening here would be better understood as we get to that point. But for now, we'll just stick with the prior approach of defining an array type. With our listings array now defined, we're going to attempt to have our Express server give us the capability to get and post changes to this mock data array. So let's head back to the index.ts file in our source folder. Like we've seen for the index routes, Express gives us the capability to create routes which refer to how different endpoints respond to client requests. We're going to create two new separate routes. A listings route, which allows us to retrieve the entire listings collection, and a delete listing route, with which we can delete a specified listing. To get the listings information in an Express route, we can do just like we've done when we sent the hello world message for the index route, or in this case, how we've sent just a message that says 1 + 2 = 3. But first, what we're going to do is we're actually going to import the listings array to actually make the data available in our index.ts file. Now, we'll use the get function in our app server instance to denote that we're creating a get request for a certain route. This route would be /listings. In our callback function, we'll declare the request parameter and the response parameter. And like we've done before, we'll specify the underscore symbol in our request parameter since we won't be using it. And our callback function will be simple and it will simply return the response.send function and just pass in the listings array as is. We won't be making any changes to the array. In our terminal, we'll now run our server. With our server successfully running and we see the console log message, we'll head to the browser and now navigate to the /listings route. We're now presented with our mock listings data array. Now we are using the JSON viewer Chrome extension that humanizes this data, makes it more readable, and adds a little bit of styling. But regardless, you should now be able to see the listings data array on the client. Let's now create some functionality that allows us to delete a listing from our mock data array. In a standard REST API, the get method is often used to request data. Though many other methods exist, we'll use the post method to specify a route that can have data be sent to the server to conduct an action. In this case, we'll look to have the ID of a listing be passed in our post request, which will be used to delete that particular listing. In order for our server to access the data in our post request, we'll look to install a middleware to help parse the request body. We're going to use the popular body parser utility library. So we'll exit the server in our terminal and then first install the body parser package as a dependency. We'll then install its type declaration file as a dev dependency. In our index.ts file, we'll now import body parser from the body parser package. To use middleware in our Express server, we'll use the app.use function that Express provides. This use function can be used in the app server instance. In our middleware function, we'll pass in bodyparser.json. This bodyparser.json function will help parse incoming requests as JSON and expose the resulting objects on request.body. We'll now set up the post request for the new delete listing routes. We'll specify the callback function like we've done before and attempt to access both the request parameter and the response parameter. Now we expect the ID of the item or listing to be deleted is to be sent as part of the request body. So we'll attempt to access that ID. Now, request is actually inferred to be of the interface type request from our Express package. But body doesn't have an explicit type. It's inferred to be of type any. As a result, the ID doesn't have a particular type here as well. So what we'll do is we'll simply try to define or explicitly define the ID variable we're creating as a string type. When it comes to actually finding the listing we want to delete, there's a few ways of doing this, but we keep it simple and we'll use a very simple for loop. Here we're saying iterate through the listings array. And at any moment in time, if that iterated listing item ID is equal to the ID from our request body, we can actually do something here. And what we intend to do is we intend to do two things. We want to actually delete that listing, but we also want to send the deleted listing. So we'll use the response.send function, but in this function, we'll pass in listings.splice, the index of the listing we want to delete. And since we want to delete a single listing, we'll just specify 1 as the second argument. The array splice function deletes an item, but it also returns the deleted item, which is exactly what we want here. Now, if we actually manage to go through the entire listings array and we don't actually find the item we want to delete, we'll get to the bottom of our function here and we'll send a simple response that says failed to delete the listing. There's a few ways we can try and make this post command happen, from building a UI to interact with the server to using tools like Postman. For now, however, we'll simply use curl in our command line to simply test this post request. Curl is installed by default on many systems and is an easy way for us to interact with APIs. OS X users should already have curl installed, but we'll also provide a link in our lesson documentation with where Windows users can download and install curl. The simplest way to use curl is to run curl followed by the URL we want to interact with. Now, since we actually have to pass data with our request, we're going to introduce some arguments into our curl request. The first one being the -x flag, which allows us to specify which HTTP method to use. We'll say post, since we intend to make a post request. We'll declare the URL of our endpoint right after. This URL is http localhost 9000/delete listing. Now, the next flag we're going to add, the -h flag, allows us to set a header for our HTTP request. We'll specify content type, application JSON, to inform the server that the body of the request is JSON. And then finally, we're going to add the -d flag to pass the body of our request. Here, we'll specify the data we want to pass within quotes. We'll pass in an ID of the particular listing that we actually want to delete. For this example, we'll just say 001, which is a reference to the first listing object in our mock listings data array. Now, to be able to run this curl command, we actually need to have our server running. So we're going to open a new tab in our terminal and then navigate down to the server directory within our Tinyhouse project. And then we'll actually run the project with npm run start. With our server running in the tab below, in the tab above, we can now actually press enter to run our curl command. We can probably see just from the result here that our curl command was successful because we actually have the returned deleted listing be sent back to us. The ID saying 001 and all the other fields about that particular listing. Now when we head to the browser, refresh this /listings route in our localhost 9000 URL, we can actually see that the first object in our listings array has now actually been deleted. We've just successfully created a GET request to retrieve all the listings, and now we've completed to create this POST request, which allows us to delete a listing from our mock data array. Now, before we close this lesson, the only thing left for us to do is we'll remove the initial GET request we set up for our index route, and we'll also remove the variables we declared needed in that route, 1 and 2. In this lesson, we're going to summarize what we've done so far. We've built a very simple Node Express TypeScript project. In the package JSON of our app, we can see the dependencies and dev dependencies our app depends on, such as the body parser and express packages as the main dependencies. And in our development dependencies, we're introducing the TypeScript ESLint packages, the ESLint package, Nodemon, tsnode, and TypeScript. We've also specified the type declaration files for our main packages, such as body parser, express, and node. We've introduced 2 scripts in our app, the start script, which allows us to start the server. We're using Nodemon because Nodemon allows us to actually detect changes in our code and will restart the server for us. And we're passing in the starting point of our app, the source/index.ts file. In the build script, we essentially allow us to compile our TypeScript code to valid JavaScript, and we're using the tsc command that TypeScript provides. The ESLint rc.json file is the file that sets up the configuration for our ESLint setup. We're using the TypeScript ESLint parser because we need to parse TypeScript code. And we're extending a plugin known as TypeScript ESLint Recommended that contains a series of recommended rules. We've also added and customized a few rules of our own. The configuration for our TypeScript compiler is in the tsconfig file. And this is where we specify items such as the root directory of our TypeScript code. In this case, we say the source folder, the output directory for where the compiled built JavaScript code should go to. And then we've also added a strict field and given it a value of true, since this field enables all the strict type checking options. The source listings file is where we actually export and create a mock data array. We've said that this array should conform to the listing array type, in which each item has to be of the listing interface type. It has to have an ID, a title, an image, an address, all of which are strings. And it has to have the price, number of guests, number of beds, number of baths, and rating, of which these fields are all numbers. The index.ts file is the main starting point of our app and is where we actually start our Node server. It's where we import the express and body parser packages, where we import the mock listings data array. We run the express function to create a server app instance. We apply middleware and pass in bodyparser.json to convey that we want all our requests to be handled as JSON, all our request data to be handled as JSON. And then where we actually declare two routes for our app. We have the /listings route, which acts as a GET request for clients, where clients can retrieve data. In this case, it just retrieves the listings array. And we have the delete listing route, which acts as a post resource, where clients can post information to actually delete a listing. This particular route expects an ID, for which in this case, we actually filter through the listings array, find the appropriate listing with the matching ID, and we actually can delete the listing here. If a listing can't be found, we simply send a message that says failed to delete listing. So what we built here conforms to a very simple REST API. We have endpoints that act as resources where the client can sort of convey and manipulate information. What we're going to do in the next coming lessons is introduce GraphQL, but we're also going to change what we've built here to maintain the same level of functionality, but to instead use a GraphQL schema. This will give us a very good introduction to see some of the advantages that GraphQL would bring.
So far, we created a RESTful API to interact with our mock data. So what is this GraphQL thing?
Well, GraphQL is a query language for APIs. GraphQL was originally created to help client-side applications dictate the data they need before they request it. We thought the best way to introduce GraphQL would be to compare a real REST and GraphQL API that achieves the same outcome.
That's right. In this module, we will explain what GraphQL is, compare GitHub's REST and GitHub's GraphQL APIs. Finally, we'll dive deeper into the core concepts of GraphQL.
What we've built so far with our Node app conforms to a little more to what a REST API is. REST standing for Representation State Transfer. In traditional REST APIs, the client interacts with the server by accessing various endpoints to get, post, put, or delete data while leveraging the HTTP protocol. In our app, to get all the listings, we had to make a request to the /listings endpoint. If we wanted our server to serve data for just one listing, we could implement a /listing/ID endpoint, where ID is a dynamic value. If we had users in our mock data, we could also implement a user/ID endpoint to serve certain user data, and so on. Now let's consider an example scenario. A client app needs to display some user information plus all the listings for that user. Now, this client doesn't have to be ours. Someone else can develop a web or mobile application that interacts with our API. How would we play out this scenario with REST? With an example REST API, the client would need to make a request to /user/ID to fetch the initial user data for that particular ID. Then the client will have to make a second request to something maybe like user ID/listings that returns all the listings for that user. So far, this isn't too bad. It's just two requests. Where does GraphQL fall in here? GraphQL is a query language for making requests to APIs. With GraphQL, the client tells the server exactly what it needs, and the server responds back with the data. GraphQL is not tied to any specific front-end or back-end technology, meaning you can use GraphQL with React, Vue, Node, Ruby, Rails, etc. Here is an example query where we attempt to query the user of a certain ID. And then when we query this user, we can tell our GraphQL API which fields we want to be returned. In this case, we're saying we want the ID field, the name field, and then for the listings for this user, we also want the ID and title of these listings. Now, GraphQL is also a typed language. So before we declare how we want each of these fields to be resolved in our backend API, we have to tell GraphQL the type of the data we expect. We want the ID to be of type GraphQL ID, the name to be of type GraphQL string. We want the listings field to be of type a list of listing types. And the exclamation mark here is basically telling our API that this is a required field. GraphQL allows for some significant benefits. GraphQL APIs are intuitive because the client specifies exactly what data it needs, thus making the code intuitive and easy to understand. GraphQL APIs are performant because no useless data needs to be transferred, and as a result, reduced latency will make our app feel faster. This is especially important for slower internet connections. And GraphQL APIs are typed. GraphQL uses a type system of its own to validate requests. This integrates beautifully with TypeScript to create a robust, statically typed application. GraphQL APIs are also self-documenting. They encourage the use of GraphQL IDEs or integrated development environments. And GraphQL APIs also consist of a single endpoint. So for all the data that might be returned from a database or a server, everything is to be served within a single endpoint in GraphQL. Listings, a certain listing, users, a certain user, etc. As we've mentioned, GraphQL isn't tied to any specific technology. This is because GraphQL is a specification, not a direct implementation. The community has created several different implementations based on the tools and technologies we might be using. For example, there's the Apollo server library for Node frameworks, GraphQL Java for Java applications, GraphQL Ruby for Ruby applications, and a lot more. And this is the same for client tools as well. There's Apollo client for the React, Vue, and other JavaScript client code that can exist. There's GraphQL Python to work with Python, GraphQL.client for .NET applications, and a lot more as well. This all might still sound pretty vague and too good to be true. So in the next lesson, we're going to go through an example-driven approach to compare a real REST and GraphQL API. We'll be using the GitHub API that has been made publicly available. And only after going through the next lesson will we come back and discuss some of the more core concepts of GraphQL. Let's dive into a good example that showcases GraphQL before we discuss and address some of GraphQL's core concepts. We're going to use the GitHub API as this lesson's example. GitHub has two versions of their API currently available to the public. Version 3 is the traditional REST API. Version 4 is their new GraphQL API. To access GitHub's REST API, we can make requests to the following public URL, api.github.com. This main parent route gives us an overview of all the different routes we can then interact with in this REST API. To explore GitHub's GraphQL API, we can go to developer.github.com/v4/explorer. For this GraphQL interface to work, we'll need to be logged in with our GitHub profile. For our first exercise, we'll assume the first thing we'd want to do from a client perspective, is to get the description of a particular repository. The repository we'll be using is GitHub's own Hello World repository, created by the Octocat profile. Here's the description we'd like to fetch from our APIs. My first repository on GitHub. When we're in this route, we're presented with the repository information in our UI. GitHub also allows us to see the data being returned for this route by hitting the api.github.com/repos/octocat/hello world route. We're essentially making a GET request here as well, but the data being returned now looks like the following. A lot of data is being returned, including but not limited to repository information, such as the name, description, details of the owner of the repository, as well as other corresponding URLs that can allow us to make other requests to get more information. Notice how the only data we want is the description line, my first repository on GitHub. Instead, the server sends us a lot more useless information. And when we say useless, we're referring to information that we don't actually want. Regardless, we have to retrieve all this information despite the fact we only want a single field. Let's contrast this with GraphQL. We'll head over to the GraphQL Explorer GitHub provides for their new API. The first thing we should mention here is that we're now able to interact with an interactive environment to actually help make GraphQL requests. We'll talk about this a little more in the next lesson, but the capability of using IDEs is a really cool feature that many different GraphQL services provide. Now, an important note to make: this deals with live production data. You can most likely run mutations here that can delete, remove your projects, repositories, and perhaps even your account. We'll suggest being careful when you use this Explorer. Though we won't be doing too much of a deep dive just yet, we essentially want to make a GET request of sorts to retrieve the description of the Hello World repository. Here, we can make a GraphQL query to retrieve what we want. There's already a query set up to allow us to retrieve the username of our account. The username here lives in the login field under Viewer. If we hit the play button, we can see the login field returns our username, tinyhouse-dev. Let's modify this query and attempt to query the description field from a certain repository. GraphQL queries are intended to be well documented and fairly easy to recognize how an API is to be shaped. The IDE here provides us with a Docs tab that allows us to explore the GraphQL API scheme. The field we want to return is a query, so we'll navigate to the query type. We can see a large number of queries that can be made here, but we're interested in querying the repository field. The repository field takes two arguments, an owner and a name, and allows us to query information about a certain repository. The only field we want from a repository is the description field. Let's see this in action. We'll specify repository as the parent field we want to query, and we'll pass in the arguments that conform to the Hello World repository we're looking at for this lesson. We'll say the owner is a string of octocat, and the name of the repository is Hello World. And we'll only declare a description field within. When we press play, we get the expected description we're looking for. Notice how clean this response is as compared to the response being returned from the REST API. We're only getting what we want. For the next exercise, let's do something a little more complicated. Imagine if we were developing a client app that needs to display the following information from a single repository. We want to display the repository description. We also want to display the title of a certain issue in the repository. And we want to display the first 5 comments of said issue. And for each comment, we'd also additionally want to display the author who made the comment, the username, and the body text of that comment. To accomplish this using the REST API, we must make 3 different requests using the GitHub API. The first request is required to get the repository description, and we'll simply hit the octocat/hello world route. The second request is required to get the title of a certain issue. GitHub's REST API allows us to add an issues subpath to the main repository URL route. We'll pick issue number 348 for the Hello World repository. And here we can see the title of the issue. The third request we're going to make is to get the comments of this particular issue. GitHub's REST API allows us to preface comments as a subpath to the issue number of the route that we just used. And from this, we can see a list of all the comments made for this particular issue. We're making 3 separate requests to get all the information we might be looking for. With a well-built GraphQL API, this can be made a lot easier. This is because with GraphQL, we can specify exactly what we need from the client. Let's see how this can work. We'll head back to the GraphQL playground that GitHub provides, and we'll look to modify what we've just done. The repository field contains another field that allows us to query information about an issue. To get information for a certain issue, we're required to specify an argument called number, where we can give it the issue number. From this issue field, we're able to query the title of said issue. We're also able to query for comments of the issue. Comments here is a paginated field, so we can query the first 5 comments by adding the first argument and giving it a value of 5. This paginated field follows a particular pattern we'll talk about later in the course, but essentially the data we're looking for lives within edges and then nodes. Now we can query what information we want from the comments. In this case, we'll look to get the comment's body text, and the username of the person who made the comment lives under author login. When we run the following query, we get exactly what we requested, no more and no less. Now, how cool is that? There's a lot of things that we've glazed over here, such as how we're actually making our queries, what are fields, what are the type definitions of each field, where do GraphQL mutations fall in this picture, and a lot more. Throughout the course, we'll be introducing all these concepts one by one, starting with the next lesson, where we take a deeper dive into some of GraphQL's core concepts. With this lesson, however, we're hoping to convey how exciting GraphQL is, since it makes interacting and retrieving data a lot cleaner from a client perspective. Now that we firsthand saw the advantages of using GraphQL in a real-world example, let's dive into some core concepts. After playing around with GitHub's GraphQL API in the previous lesson, we know that the GraphQL query language allows us to select properties on object types. For example, querying something like this, a listing object type that has a title and a price field, would allow us to gain data like this, where title and price return some information. But how do we know that the listing object type has a title or price property? Does it have more properties we can select? This is where the GraphQL schema comes in. Every GraphQL API has a schema which completely describes all the possible data we can request. Another good way to look at it is that the schema is the blueprint of a GraphQL API. When a request comes in, it's validated against that schema and processed accordingly. How does fields in the schema get processed? That's due to the second piece of a GraphQL API, the resolvers. Resolvers are functions that turn a GraphQL operation or request into data. We'll first talk about a GraphQL schema before we dive into discussing the topics within GraphQL resolvers. The most basic components of a GraphQL schema are the object types, which represent some kind of object we can query and what properties that object has. In the previous example, we could have an object like so. This type definition says this is an object type called listing. This listing object has a property called ID, which is a GraphQL ID. It also has a property called title, which is a string, address, which is also a string, and price, which is an integer. The definitions at the end of these fields refer to the type that is to be returned from these fields. The title field is expected to return a string, the address field is expected to return a string, and so on. The syntax we're looking at here is known as the GraphQL schema language. And we're going to talk about this some more as we start to introduce it into our Node application. A GraphQL schema allows us to develop relationships between different object types. For example, we can say the listing object type can have a tenant field in which tenant is to be an object type of its own. For example, a user object type. Similarly, the user object type can have a similar but inverse relationship of its own, where it can contain a listing field that is to be the listing object type. These are sort of one-to-one relationships where listing can return a particular user and the user can return a particular listing. We could also have one-to-many relationships where we can example say the user object type has a listings field that return a list of listings. In the GraphQL schema language, we can define a GraphQL list by using the square bracket syntax here, which states we're returning a list of the listing object type. There are two special object types within a GraphQL schema called the query and mutation object types. Every GraphQL schema must have a query type and may or may not have a mutation type. Query and mutation represent the entry points of every GraphQL query. The purpose of a query type is to define all the possible entry points for fetching data. The purpose of the mutation type is to define all the possible entry points for manipulating data. Here's an example of a query object type that allows us to query a field known as listings. Similarly, we can have a mutation object type that has a field labeled delete listing, which takes ID as an argument and, according to its name, would most likely delete a listing. The listings query and delete listing mutation both return variations of the listing type that we could have defined earlier. A GraphQL object type has one or more properties, but at some point, these properties must resolve to some concrete data. That's where the scalar types come in. They represent basic data types that do not have any more nested properties. GraphQL comes with a set of default scalar types out of the box. Boolean, true or false, int, assigned 32-bit integer, float, assigned double precision floating point number, in other words, a decimal number, string, a UTF-8 character sequence, ID, which is similar to string, but it's used to represent a unique identifier in GraphQL, which is basically an identifier which is not intended to be human readable. Notice how some of these types are very similar to the basic types in TypeScript. Enumeration types are a special kind of scalar type that are restricted to a defined set of allowed values. For example, let's say we wanted to add a listing type property for our listing object type, and we wanted to say the listing type can only be either a house or an apartment. This is where we can use an enumeration type to restrict the property to be one of these values. Objects, scalars, and enums are the only types we can define in GraphQL, but we can apply additional modifiers to affect their behavior. For example, let's say the listing object type is to have a bookings field. You've already seen this before, but in this particular case, we're specifying the return to be a GraphQL list, which is denoted by the square brackets here in the GraphQL schema language. So we're stating that the bookings field is to return a list of values in which the values are to conform to the booking object type. Now, one thing that we've glazed over that we haven't actually mentioned yet, notice that we haven't introduced any exclamation marks here. The exclamation mark refers to telling GraphQL that these fields have to conform to these types. In other words, these fields have to be required and can't be null values. In this case, we're saying that the bookings field could be a null value, and the returned items within the array or list could also be a null value. When we look back at the other example we had before, by using the exclamation mark twice, we're saying we always expect a list with zero or more items, but in the particular list, we always expect every item to be defined as the listing type. Just like functions in any other programming language, we can pass arguments to fields. This is because fields are conceptually functions that return values. What if we needed to pass in multiple values to a createListing GraphQL field that will be able to resolve the intended result, which is have a listing be created? Just like we can pass in multiple arguments in a JavaScript function, we can pass in multiple arguments to a GraphQL field. In this case, we're saying this particular field expects the ID, title, address, and price arguments, and these are their respective types. Now, good convention will often find us creating input object types in situations like this, often valuable in the case of mutations, where we might want to pass in an entire object to be created. In the GraphQL schema language, input types look exactly the same as regular object types, but with the keyword input instead of type. In this case, we're saying the createListing field now takes a non-nullable input argument of type createListing input. We've come to understand that a GraphQL schema lays out the blueprint of how a GraphQL API is to be shaped. But how do these fields return values or make the changes we expect them to? We've mentioned this earlier, but this is where GraphQL resolvers come in. Resolvers are essentially functions or methods that resolve the value of a GraphQL field or GraphQL type. Every field in a GraphQL API is referenced with a resolver function responsible in returning the value of that field. For the original listings query we had in mind, our resolver can simply be a function that returns an array of listings that might have been defined elsewhere. The delete listing mutation resolver could have some additional functionality with regards to making the deletion before returning the expected value. And just like how these root level fields in the root mutation object types have the resolvers, the fields within the custom object types we can create have their own resolvers as well. For example, in this case, we can say the ID is to resolve to an ID within an object, title is to resolve to title within the object. These are known as trivial resolvers, since we're returning simply values within the passed-in object that is equal to the name of the field that we're actually declaring. So with that being said, you might be wondering what these objects or arguments or context arguments within the resolver function is. A GraphQL resolver would always receive 4 positional arguments. The first one is the object returned from the resolver on the parent field. For the root query and mutation object types, this argument is often not used and undefined. The second argument is the arguments provided to the field. The third argument is known as context, which is a value provided to every resolver and usually holds important context information. For example, the state of the currently logged in user. And finally, the fourth info argument is usually only used in advanced cases, but it contains information about the execution state of the query, such as the field name, the schema, the root value, etc. This introductory lesson only touches some of the main core concepts of GraphQL to give us a head start as we proceed. There are numerous other topics, both advanced and non-advanced, like pagination, caching, union types, interfaces, and so on. However, this will be more than enough to get us started and well on our way for the next couple of lessons. Keep in mind, we're going to reintroduce these topics as we begin to use them in the course.